Good morning. So last week we were talking about hypothesis testing, which is the maths of spotting when something is a bit fishy, when something isn't what we expect it to be or what we think it's to be. So let's pretend that I work in an egg factory, and that egg factory breaks 15% of the eggs it processes. Now that's quite high, but stick with me. So I'm boxing up these eggs into packs of 12. And so I could say, right, in any pack of 12, the number of broken eggs is a discrete random variable. I'm going to call it x, and it will follow a binomial probability distribution where n is 12 and p is 0.15. Now let's pretend that I have a horrible feeling that actually I'm breaking a lot more than 15% of my eggs. So what I'm going to do is I'm going to do a hypothesis test where my null hypothesis is that the probability is 0.15. And so that's the probability that I use. So I'm not using a different probability that I'm using that, going to use p as 0.15 as my probability. But I think that actually it might be bigger than. And we have problems where we think it might be bigger than, or problems where it might be smaller than. And we need to make sure we look at the right tail, don't we? So here's a sort of sketch of the graph of probabilities, not to scale, okay, so just forgive me for sort of enlarging that middle bit. I know my peak is going to be 12 times 0.15 is 1.8, so I'm expecting to mostly get 2 broken eggs in a packet. But what about if I get 3 or 4 or 5? Is that enough evidence to suggest that actually the probability is greater than 0.15 of breaking eggs? Well, let's test at the 5% significance level. And that means that I'm testing to see if the probability of a value or greater than that value is 0.05. And if it's less than that, then alarm bells will start to ring. Okay, so I am going to enter my values in my calculator. So I'm going to firstly test for 3 or more. Okay, so I've got my number of trials and my probability in. I'm looking at the upper tail because I fear the probability is greater than 0.15, so I'm looking at this upper tail. So let's work out the probability of that. So I go lower is 3, upper is 12. That's my probability. That's a big probability in comparison with that. So I'm okay, I'm not worried if I'm getting 3 broken eggs in a pack. What about if I'm getting 4 broken eggs in a pack? What about that probability there? So let's now go to a lower of 4, still an upper of 12. Now that's getting smaller, isn't it? If I'd been testing at the 10% significance level, I would start to say, right, this is getting fishy. But I'm not. I'm testing at the 5% significance level, which is a level that requires more proof. You need more convincing that things are different. So I'm not suspicious at that point there. But what about if it is 5 or bigger? So let's look at that probability. Still upper of 12, obviously. I've dropped below 0.05. So if I get 5 broken eggs in a packet, then I start to get to the point where I say, right, I reject the null hypothesis, and we have sufficient evidence to suggest that the probability might be greater than 0.15. And so 3 broken eggs in a packet, not worried. 4 broken eggs in a packet, not worried at the 5% significance level. 5 broken eggs in a packet, worried. 5 is the first value that causes me to worry, and we call 5, in this case, the critical value. And this shaded area here, let me switch to red, this shaded area here is known as the critical region. So obviously any value greater than 5, 6, 7, 8, 9, 10, 11 or 12 will give us a similar conclusion that we can reject that and we have sufficient evidence to support that. So today we are talking about finding critical values and critical regions using hypothesis. Okay, so 2 questions. Here's the first. This is one of these contextless questions, so it doesn't tell you what we're dealing with. It's just something that's happening 10 times that follows a binomial distribution. And at the moment we think the probability is 0.2, so I would like to write it out like that because that's what I'm going to type in on my calculator. We have a feeling though that the probability might be bigger than that, so we're going to test to see if that feeling is correct. So here's my probability distribution. Of course it's not symmetrical, is it? The peak for this 10 times 0.2 is 2, so actually it should be really sort of skewed this way. So, but anyway, I'm testing at the 5% significance level, so I want to know what's the first value here that makes this probability less than 0.05. So we want to know the first value that makes the probability go below that. And so let's have a look at that problem on our calculator. So let's type in the data. So it needs to be 10 as our number of trials, and probability of success 0.2. It is an upper tail problem, so my upper is always going to be 10, and I'm going to vary this value. So I know the peak is at 2, so let's try 3. So from 3 to 10, is this value 3? Well, no, that's quite a big probability, isn't it? So that wouldn't be suspicious. So this value here, this critical value, has to be bigger than 3. So let's try 4. What if it's 4? Okay, smaller probability, but still not low enough to ring alarm bells. So 4 is okay. And let's try 5. Ah, right, look. When I set the probability to 5 to 10, I get a probability that's less than 0.05. The good thing about these questions is that we're dealing with discrete data, so there's no decimals involved. It's either 4 or it's 5 or it's 6. In this case, we're saying that these probabilities are below that. So my critical region is this region here. My critical value is 5. Question this time though wants the critical region. So the critical region is when my value x, and we don't know what x is, no context, is greater than or equal to 5. I suppose you could say, well actually you ought to say this, because it can't be bigger than 10, but we tend to write it like this because we've already said that, right, it can't be bigger than 10. But that would be okay, that wouldn't be wrong. All right, so here's the second question, which introduces context. So this is a bit more sort of, we can see what's going on here. So we've got a mechanical component fails on average 3 times out of every 10, 3 out of 10, 0.3. So we're talking about a probability of failure of 0.3, and the manufacturer is testing a sample of 20 components. So I'm straight away going to write that down. That's just the first thing I look to write down is, these are my parameters that I'm working with. Now we've got some interesting questions here. So the test statistic is this, isn't it? We are measuring in this case how many of the 20 components have failed. So the test statistic is the number of failed components. That's what we're going to count each time. The null and alternative hypotheses. So our null hypothesis is that the probability is 0.3. But what's the alternative hypothesis in this question? Well, the engineer has designed a new system of manufacture that he believes reduces the likelihood of failure. So he's hoping that he's managed to reduce the probability of failure. So that is the answer to B. we're now going to test that at 5% level of significance. So here we go. 0, 20. 20 times 0.3 is 6, so I know my peak is 6. I think the probability is, I'm hoping the probability is less than 0.3, so this time I'm looking for a lower tail. So the questions we did last week, you were given a value when you were asked, is that enough to reject the hypothesis? With these critical value and critical region questions, we're being asked to find the value that makes us suspicious. So we now need, and we're testing at the 5%. So now there's an extra little bit in this question which I think makes it really ambiguous. I've said very clearly that the critical value is the first value that makes the probability less than this. It's a bit ambiguous here, isn't it, the way they've said that? Because you could say, well, you know, that means you could have a probability that's slightly bigger. But let's have a look and see what happens when we enter these values. So we are going to enter n is, sorry, go back, n is 20 and p is 0.3. It's a lower tail problem, so my lower is always going to be 0, and I'm going to vary this value here. My peak is at 6, so I know it's got to be less than 6, so let's try 5. Really big, nowhere near that, so this is not 5. So let's bring it down to 4. What about if I find 4 failed components? Is that enough to think that I've improved the process? Come down, but it is still small, but I'm going to make a little note of that probability. So when x is less than or equal to 4, 0.2375, just because of this slightly ambiguous thing here. Okay, let's try 3. Okay, x is less than or equal to 3. Still okay, we're still above 0.05. But I'm going to make a note of that there. Let's now try 2. Bingo. So 2 is the first value that drops below 0.05. So the critical value here is 2. I didn't have to worry about this ambiguous thing here because this is closer to 0.05 than this. So does it ask for the critical value or the critical region? It asks for the critical region. Okay, so the critical region is that x is less than or equal to 2. Anything in that range there, I'm going to say, right, I reject that. I have evidence to suggest that this is true. New question. Write down the actual significance level of the test. Well, 0.05 is 5%. We've actually got a probability here of 0.0355, which is 3.55%. So that's the actual significance level of this test, 3.55. This probability here wasn't 0.05, it was 0.0355. So that's the actual significance level of the test. Okay, just 2 questions to try from the textbook, page 104, exercise 7b. Question 5, and then that's a straightforward sort of non-contextual one, and then question 8. Now, why am I only giving you 2 questions from a big exercise? Well, there's one more thing we need to cover, and that's tomorrow. So I'm having to choose my examples carefully. Question 8 is a context question. Part C in question 8 is another way of asking what we just answered in part D, the actual significance level of the test. And I might just talk about that in tomorrow's video as well. So just those 2 questions, question 5 and question 8 on page 104, exercise 7b. And then the final part of this comes tomorrow.